So before we move on with enzyme kinetics, I want to just make sure we really define certain parameters. So really, kinetics is the study of the rate of change of a reactant to a product. How fast you can convert A to B. That's what kinetics is. There are useful parameters used in enzyme kinetics. The first one is called velocity. And essentially, velocity means the change of substrate concentration per unit time. How much substrate is consumed or how much product is produced per unit time. That's how velocity is expressed. Alternatively, there's something called rate, which expresses the total amount of substrate changed, converted per unit time. The most useful one here is velocity. We will talk about that a lot. Change in concentration of substrate or product per unit time. Initial velocity is an important parameter which is best described as when an enzyme reaction begins. Early in that reaction, early in time, early in that reaction, it gets, there's not enough substrate consumed or not enough product consumed, produced. It means the reaction is in a linear phase. The enzyme reaction, catalyzed reaction, is in a linear phase, and that's typically called the initial velocity. Okay, I'll explain that a little later on again. So there are actually two important scientists that together came up with a treatment of enzyme kinetics. And that treatment made some assumptions. First of all, is that, and these guys are Michaelis-Menten, and they basically said when ES is formed, it stays constant or in a steady state in the linear phase of the reaction. The other assumption they made is that if you have an excess of substrate, a large excess, then all the enzyme is saturated with the substrate and the enzyme is working at maximal velocity. And that is known as Vmax. Okay? It can't work any faster. And Vmax, by definition, is given this formula. It's not that really crucial, but understand that Vmax of any enzyme is when the enzyme is completely saturated with substrate. Okay? So, besides the Michaelis-Menten treatment of enzymes, there's another group of enzymes that do not follow Michaelis-Menten. Okay, kinetics. So these are going to be called allosteric enzymes. So I'm going to explain the difference for you in a minute, but I'm going to start with the allosteric enzymes, then go back to the Michaelis-Menten. Okay, so I want you to appreciate there are two types of enzyme kinetics that we will treat. The first one is the one I just mentioned to you. Here's an enzyme reaction, velocity. Here's as a function of substrate concentration. This blue line is a representative enzyme that follows Michaelis-Menten. It starts kind of in a linear phase and then eventually saturates at Vmax. Okay, we'll get back to that shortly. There's another enzyme in the green trace, and I want you to notice this is a sigmoidal S-shaped curve, completely different than the blue trace, the Michaelis-Menten. When you see an S-shaped curve for an enzyme, velocity over substrate, you know that this is an allosteric enzyme. That means this enzyme is regulated by small organic molecules that are not the substrates, distinct molecules that bind to an allosteric site and change the velocity of the enzyme. So I'm going to talk about the allosteric enzymes right now and then go back to the Michaelis-Menten. So how are allosteric enzymes regulated? There are two ways you can regulate an enzyme allosterically. I'm going to start here with A. Here's an enzyme, an allosteric enzyme. Again, you note this S-shaped curve. They all have S-shaped curve. If you add a molecule, a small molecule that binds to an allosteric site, a site other than the substrate binding site, that positively modulate the activity of this allosteric enzyme, it could change the Vmax by increasing it, the velocity. Okay? That's a positive allosteric activator. If you add a molecule that decreases Vmax, it could decrease Vmax, like the bottom trace, that would be a negative allosteric effector. There's another way that allosteric effectors can change enzyme activity, which is shown down here. So there's either changing Vmax positively or negatively. The bottom graph shows you that the amount, here's the normal enzyme, allosteric enzyme. If you add a positive effector, note how it shifts the curve to the left. What that tells you is the enzyme needs less substrate to start catalyzing that substrate. Okay? So that's a positive allosteric effector. Conversely, there may be negative allosteric effector that shifts the kinetic curve, the allosteric curve, to the right. That means the enzyme needs more substrate before it works on it. So allosteric enzymes can be regulated by either A or B, not together. You can't regulate the same enzyme in both ways. You either change Vmax, like in A, or you change the affinity, if you want, of the enzyme for its substrate by increasing it by shifting the curve to the left or to the right. Okay? That's all we're going to say about allosteric enzymes. But I want you to appreciate all allosteric enzymes will have an S-shaped curve, very different from the Michaelis-Menten curve, and these are the ways their activity are changed, either changing Vmax or changing the amount of enzyme needed for that amount of substrate needed for that enzyme to work. Reducing it by shifting to the left or increasing it by shifting to the right. If you like this video, please subscribe. Thank you.